a single atom, invisible to the naked eye, a ghost of existence, yet the foundation of all reality. It is the simplest unit of matter, the indivisible building block of all things. But within its structure lurks a force so immense that, when unleashed, it can bring about unthinkable destruction. It is both the seed of creation and the harbinger of annihilation. The atom is a paradox, a force of life and death, of stability and chaos, of permanence and decay. For centuries, humanity sought to understand what the universe was made of. The ancient Greeks first proposed the idea of the atom as the smallest, indivisible unit of matter. Democritus, the philosopher, imagined these particles as eternal and unbreakable, solid spheres that made up all things. He could never have predicted that the true nature of atoms was far more complex, far more unstable, and far more dangerous than anything his mind could conceive. The modern atomic model is a marvel of scientific discovery, built on centuries of experimentation and relentless curiosity. With the dawn of quantum mechanics, physicists uncovered a hidden world within the atom, a reality governed not by certainty, but by probabilities and strange, almost mystical rules. Electrons flicker in and out of existence. Particles behave as both matter and wave, defying intuition. Forces of attraction and repulsion hold atomic structures together in an eternal dance, a delicate balance of order and chaos. But nestled within the atom's core lies something even more profound: energy, bound by the strongest forces in the universe. This energy is what holds the atomic nucleus together, overcoming the repulsive forces of its positively charged protons. It is the glue of reality, the reason atoms do not simply fly apart. Yet, as powerful as this force is, it is not invincible. When the right conditions arise, when an atom becomes unstable, when a neutron strikes at just the right angle, the very glue that binds it together can be turned against it. And what follows is nothing short of cataclysmic. The discovery of this hidden power forever changed the course of human history. The ability to split an atom, to break apart what was once thought unbreakable, unleashed an energy unlike anything the world had ever seen. In an instant, entire cities could be reduced to ash. The sky itself could burn. The very energy that sustains the universe could be wielded as a weapon, turning the fundamental building blocks of life into agents of destruction. But atomic destruction is not limited to the horrors of war. It is a force woven into the very fabric of existence. Even without human intervention, atoms are not eternal. Some decay over time, their structures crumbling from the inside out. Radioactive decay is a whisper of instability, a quiet unraveling that occurs on scales of time ranging from fractions of a second to billions of years. The most stable of elements still succumb to entropy in the end, giving up their energy, breaking apart, dissolving into nothingness. And beyond the confines of our world, on the grandest scale imaginable, this destruction extends to the fate of the universe itself. Every star, every planet, every galaxy, composed of countless atoms, faces an unavoidable end. The force that holds atoms together is not eternal. The balance between creation and destruction is precarious. One day, in the far reaches of cosmic time, even atoms themselves will cease to exist. The very essence of matter, once thought indestructible, will fade away. The universe, once filled with light, structure, and order, will become cold, empty, and lifeless. But could there be something beyond this final fate? Could there be a form of atomic existence that defies destruction? Science has begun to explore the possibility of exotic matter, strange theoretical particles that may endure beyond what we consider possible. Could such matter hold the key to an escape from the doom of entropy? Could it offer a new beginning, a way for matter to persist beyond the slow unraveling of all things? This documentary is a journey into the paradox of the atom, a journey into the hidden power within matter, a journey into the inevitable destruction woven into its very nature. From the discovery of nuclear fission to the decay of the last atoms in a dying universe, we will explore the dark side of atoms, their ability to build and to destroy, to create and to annihilate. In understanding them, we uncover not just the nature of matter, but the ultimate fate of existence itself. The road to understanding the destructive power of the atom began with an innocent pursuit of knowledge. For centuries, scientists believed that atoms were the smallest, indivisible components of matter. But as the 19th century gave way to the 20th, new experiments revealed a far more intricate reality. The discovery of subatomic particles, protons, neutrons, and electrons, suggested that the atom was not a solid, unbreakable sphere, but rather a miniature universe in itself. The journey towards splitting the atom began with the pioneers of atomic theory. In the early 1900s, Ernest Rutherford conducted experiments that changed the way scientists understood the atom. By bombarding gold foil with alpha particles, he demonstrated that atoms were mostly empty space, with a tiny, dense nucleus at their core. This nucleus contained the majority of an atom's mass and was held together by a mysterious, immensely powerful force. As physicists delved deeper into the structure of the atom, they uncovered even more perplexing truths. Quantum mechanics emerged as the key to understanding atomic behavior. Unlike the predictable mechanics of classical physics, quantum physics revealed a world of probability, where particles could exist in multiple states at once, and where energy could be harnessed in ways previously unimagined. Then came a discovery that would change everything: nuclear fission. In 1938, German scientists Otto Hahn and Fritz Strassmann observed that when uranium atoms were bombarded with neutrons, they split apart, releasing vast amounts of energy. The implications were staggering. This was not a small release of energy, like a chemical reaction. This was something orders of magnitude more powerful. When a single uranium nucleus split, it released additional neutrons, which could strike other uranium nuclei, triggering a chain reaction. This revelation set off a race among the world's leading scientific minds. The potential applications of nuclear fission were immediately clear: a new energy source that could power the world, or a weapon of unimaginable devastation. The world was about to enter the atomic age, an era where the very building blocks of the universe could be harnessed for creation or destruction. What followed was one of the most secretive and intense scientific undertakings in history: the Manhattan Project. Under the cover of war, some of the brightest physicists, including J. Robert Oppenheimer, Enrico Fermi, and Richard Feynman, worked feverishly to unlock the secrets of nuclear power. They sought to refine fissionable material, perfect chain reactions, and construct a device capable of unleashing the atom's destructive potential. Their success culminated in the first nuclear test, codenamed Trinity, in July 1945. As the explosion lit up the desert, the world changed forever. The fireball of an atomic blast was unlike anything humanity had ever seen, a release of energy so intense it rivaled the sun itself. The destructive power hidden within the atom had been set free. The atom, once seen as a fundamental unit of stability, had proven to be a gateway to the most powerful forces in existence. The knowledge that followed reshaped geopolitics, science, and human understanding. Nuclear fission had been tamed, for better or for worse. But this was only the beginning. The deeper scientists explored the atom, the more they realized that even greater forces lurked within. Forces that could one day decide the fate of the universe itself. The development of the first controlled nuclear chain reaction was achieved in 1942 by a team led by Enrico Fermi at the University of Chicago. Known as Chicago Pile 1, this crude nuclear reactor proved that sustained nuclear reactions were possible. It was an unprecedented leap in scientific progress, demonstrating that energy could be extracted from the very heart of matter itself. This breakthrough laid the foundation for both civilian nuclear power and the construction of the most powerful weapons ever devised. Following this discovery, the world plunged into an era of nuclear tension. The detonation of nuclear bombs over Hiroshima and Nagasaki in 1945 showcased the terrifying reality of atomic power. Nations raced to build their own nuclear arsenals, and the Cold War was marked by a precarious balance of power, dictated by the threat of mutually assured destruction, MAD. The presence of nuclear weapons reshaped global politics, forging uneasy peace through the specter of annihilation. The world had entered the atomic age, an era where human survival depended on the restraint of those who held the keys to nuclear fire. At the same time, scientists sought ways to harness nuclear fission for peaceful purposes. The post-war world was desperate for new energy sources, and nuclear power seemed to offer an almost limitless supply of electricity. The first commercial nuclear power plant, Calder Hall in the United Kingdom, became operational in 1956, signaling a shift toward using atomic energy to fuel human civilization rather than destroy it. Soon, nuclear reactors were built across the globe, promising cleaner and more efficient energy production. Yet, even as nuclear reactors began supplying electricity to cities, the inherent dangers of fission were evident. The specter of nuclear disaster loomed over every power plant. Accidents like 3 Mile Island, 1979, Chernobyl, 1986, and Fukushima, 2011, demonstrated that fission was not so easily tamed. Reactor meltdowns released catastrophic levels of radiation, rendering vast areas uninhabitable and leaving generations exposed to the deadly effects of radiation poisoning. Despite these disasters, nuclear energy remained one of the most efficient and energy-dense power sources known to humanity. A single kilogram of uranium-235 could release as much energy as nearly 3 million kilograms of coal. Governments and scientists continued refining nuclear reactor designs, improving safety mechanisms, and reducing the risks of meltdown. Meanwhile, the nuclear arms race escalated, reaching a terrifying climax in the 1960s with the development of thermonuclear bombs. These hydrogen bombs, far more powerful than the fission-based atomic bombs, relied on a second-stage nuclear reaction, fusion. The most powerful nuclear weapon ever detonated, the Tsar Bomba, unleashed an explosion equivalent to 50 megatons of TNT, producing a fireball so immense that it could be seen from over 600 miles away. The world was caught in a paradox. Nuclear technology had the power to provide limitless energy, yet also held the potential to end civilization in an instant. The Cuban Missile Crisis of 1962 was a chilling reminder of how close humanity had come to total annihilation. It was only through diplomacy and sheer luck that a full-scale nuclear war was avoided. By the late 20th century, as Cold War tensions began to thaw, new international agreements sought to limit the spread of nuclear weapons. Treaties like the Nuclear Non-Proliferation Treaty, NPT, of 1968 attempted to prevent new nations from acquiring nuclear weapons while promoting peaceful nuclear energy. But the world remained, and still remains, at risk. Nuclear stockpiles persist, rogue states seek atomic capabilities, and the question remains, will humanity control nuclear power, or will nuclear power control humanity? As research into atomic physics continued, scientists realized that fission was just the beginning. There were even greater forces lurking within the atom, forces that would push humanity to explore the next frontier of nuclear science: fusion, the very reaction that powers the stars. The promise of fusion was immense. Unlike fission, which relied on splitting heavy atomic nuclei, fusion involved forcing lighter nuclei to merge. This process occurred naturally in the hearts of stars, where hydrogen atoms fused to form helium, releasing enormous amounts of energy in the process. Scientists theorized that if fusion could be harnessed on Earth, it could provide an almost limitless source of clean energy, with minimal radioactive waste and no risk of runaway chain reactions. The dream of a future powered by fusion became the focus of intense research. The first significant step toward unlocking fusion's potential came with the development of the hydrogen bomb in the early 1950s. Unlike atomic bombs, which relied solely on nuclear fission, hydrogen bombs used fission as a trigger to create the extreme temperatures and pressures necessary for fusion. The resulting explosion was orders of magnitude more powerful than anything previously seen, proving that fusion energy could be unleashed, but only in the form of a devastating weapon. Harnessing fusion for peaceful energy production proved to be far more difficult. Unlike fission, which could be sustained in a reactor by carefully controlling a chain reaction, fusion required conditions that replicated the extreme environment inside a star. The atoms had to be heated to millions of degrees, transforming them into a superheated plasma, a state of matter where electrons and nuclei move freely, uninhibited by atomic structure. Efforts to control nuclear fusion led to the development of experimental reactors, such as the tokamak, a device designed to contain plasma using powerful magnetic fields. The idea was to sustain fusion long enough to extract usable energy. Early experiments in the 1960s and 1970s demonstrated that fusion was possible in a controlled setting, but only for fractions of a second. The problem was keeping the plasma stable long enough to make fusion a viable energy source. Over the decades, fusion research continued, culminating in international projects like ITER, the world's largest nuclear fusion experiment. Located in France, ITER represents a collaborative effort by some of the world's leading scientific nations to finally make fusion power a reality. The goal is to create a self-sustaining plasma reaction that produces more energy than it consumes, a milestone known as ignition. But despite these advances, nuclear fusion remains elusive. The energy required to initiate and maintain fusion reactions still exceeds the energy produced. Technical challenges such as plasma instability, material degradation from extreme heat, and the immense cost of fusion research have slowed progress. Some scientists predict that commercial fusion energy could still be decades away, while others believe that breakthroughs in laser confinement or alternative reactor designs might accelerate the timeline. While fusion represents a hopeful future for clean energy, its potential remains unrealized. In the meantime, fission reactors continue to provide a significant portion of the world's electricity, despite their risks. The debate over nuclear power persists. Should we continue refining fission technology with its inherent dangers, or should we pour all resources into the pursuit of fusion, even if a working reactor is still beyond our grasp? The story of atomic power is far from over. The atom, with all its potential for creation and destruction, remains both a marvel and a menace. Whether it ultimately leads to our salvation or our downfall will depend on how we choose to wield its power. Atoms, despite their fundamental role in shaping the universe, are not eternal. Their very nature dictates that over time they break down, transforming into new elements or releasing their energy in bursts of radiation. This process, known as radioactive decay, is one of the most mysterious and essential forces in the cosmos, responsible for both creation and destruction on a massive scale. At the heart of radioactive decay lies the concept of atomic instability. Some atoms are stable, holding their structure indefinitely. Others, however, are doomed from the moment they form, their nuclei destined to change, disintegrate, or even split apart. The reason for this instability lies in the balance of forces within the atomic nucleus itself. Protons, all positively charged, naturally repel each other. Neutrons act as a buffer, helping to hold the nucleus together through the powerful but delicate nuclear strong force. When this balance is disrupted, the nucleus becomes unstable, setting the stage for decay. The process of decay is not uniform. It manifests in different forms, each with its own unique properties and consequences. Alpha decay, one of the simplest forms, occurs when an unstable nucleus ejects a cluster of 2 protons and 2 neutrons, a helium nucleus. This process reduces the atomic number of the element, transforming it into a completely new substance. Beta decay, on the other hand, involves the transformation of a neutron into a proton and the ejection of an electron, subtly altering the composition of the atom while preserving its overall structure. Perhaps the most mysterious and dangerous form of radioactive decay is gamma radiation. Unlike alpha and beta decay, which involve the emission of particles, gamma decay releases pure energy in the form of electromagnetic waves. These waves, highly penetrating and incredibly energetic, can pass through most materials, making them one of the most hazardous forms of radiation. The concept of half-life is key to understanding radioactive decay. Every radioactive element has a half-life, a fixed period in which half of a given sample will decay. Some isotopes, like carbon-14, have half-lives measured in thousands of years, making them useful for dating ancient artifacts and fossils. Others, like uranium-238, persist for billions of years, subtly shaping the geological and cosmic landscape. Then there are isotopes with fleeting half-lives, existing for mere fractions of a second before vanishing into new elements. But radioactive decay is not just a destructive force. It plays a crucial role in the cosmos, fueling the heat of planets, driving the life cycles of stars, and even influencing biological evolution on Earth. The very energy that sustains our planet's core and generates its magnetic field is largely due to the slow decay of radioactive isotopes buried deep within. Without this constant energy source, Earth's interior would have cooled long ago, and with it, the geologic activity that makes life possible. Yet this slow disintegration is also an ever-present reminder of the impermanence of all matter. Atoms, even those seemingly eternal in their stability, will one day succumb to entropy. The very elements that compose the world around us were forged in the hearts of ancient stars, and through radioactive decay, they continue to evolve, shaping the destiny of the universe. Understanding this process is not merely a scientific endeavor, it is a glimpse into the fundamental nature of existence itself. Radioactive decay is not just a process that occurs in isolation. It is a fundamental mechanism that has shaped the universe itself. From the earliest moments of cosmic history to the present day, the breakdown of unstable atoms has influenced everything from planetary formation to the conditions necessary for life. It is a slow but relentless force, one that continues to sculpt the very fabric of reality. In the aftermath of the Big Bang, the universe was filled with a chaotic sea of subatomic particles. As the cosmos cooled, these particles began forming the first atoms, including hydrogen and helium, the two simplest and most abundant elements. However, heavier elements, like carbon, oxygen, and iron, did not exist in these early stages. They had to be forged in the nuclear furnaces of stars through a process called stellar nucleosynthesis. Yet even these newly formed elements were not entirely stable. Many of them contained too many or too few neutrons, making them radioactive. This instability set into motion a chain of events that would define the evolution of the cosmos. As radioactive isotopes decayed, they released energy, shaping the internal dynamics of planets, heating their cores, and influencing atmospheric conditions. Some of the most crucial elements for life, including potassium-40 and uranium-238, are radioactive and have played a direct role in the development of Earth's environment. One of the most significant ways radioactive decay has influenced the Earth is through its impact on planetary geology. The slow decay of elements like uranium, thorium, and potassium deep within the Earth's mantle has been responsible for maintaining geothermal activity for billions of years. This heat drives plate tectonics, which in turn influences everything from the formation of mountains to volcanic eruptions and earthquakes. Without the heat generated by radioactive decay, the Earth's interior would have solidified long ago, leading to a geologically stagnant world devoid of the dynamic processes that make life possible. But the role of radioactive decay extends beyond just geology. It has also been instrumental in the emergence of life itself. The constant exposure to radiation from naturally occurring isotopes has contributed to genetic mutations over millions of years, driving the process of evolution. While high doses of radiation can be lethal, low levels of background radiation have been a subtle but persistent factor in the diversification of life on Earth. By altering DNA, radiation-induced mutations have provided the raw material for natural selection to act upon, allowing species to adapt to their environments and evolve over time. In addition to shaping life on Earth, radioactive decay has been a key player in our understanding of time itself. The science of radiometric dating has allowed scientists to determine the age of ancient artifacts, fossils, and even the planet itself. By measuring the decay of isotopes like carbon-14, potassium-argon, and uranium-lead, researchers can estimate the age of organic materials and geological formations with remarkable accuracy. This has provided invaluable insights into the history of our world, from the extinction of the dinosaurs to the timeline of human civilization. Despite its many natural and beneficial roles, radioactive decay also presents a significant hazard. The radiation emitted during decay processes can be highly dangerous to living organisms. Alpha particles, though relatively weak in penetration, can cause severe damage to cells if inhaled or ingested. Beta particles, being more penetrating, can pass through skin and damage internal tissues. Gamma radiation, the most dangerous of all, can penetrate deep into the body, altering cellular structures and increasing the risk of cancer. This dual nature of radioactive decay, as both a creative and destructive force, is evident in its role in nuclear energy. While controlled radioactive decay is harnessed in nuclear reactors to generate electricity, uncontrolled decay can lead to catastrophic events like nuclear meltdowns. The disasters at Chernobyl and Fukushima serve as grim reminders of what happens when the delicate balance of nuclear reactions is lost. The release of massive amounts of radiation during such events can render entire regions uninhabitable, contaminating air, water, and soil for generations. Despite these dangers, the use of radioactive materials in medicine, industry, and scientific research has provided immense benefits to humanity. In medicine, radioactive isotopes are used in imaging techniques. Like the first significant step toward unlocking fusion's potential came with the development of the hydrogen bomb in the early 1950s. Unlike atomic bombs, which relied solely on nuclear fission, hydrogen bombs used fission as a trigger to create the extreme temperatures and pressures necessary for fusion. The resulting explosion was orders of magnitude more powerful than anything previously seen, proving that fusion energy could be unleashed, but only in the form of a devastating weapon. Harnessing fusion for peaceful energy production proved to be far more difficult. Unlike fission, which could be sustained in a reactor by carefully controlling a chain reaction, fusion required conditions that replicated the extreme environment inside a star. The atoms had to be heated to millions of degrees, transforming them into a superheated plasma, a state of matter where electrons and nuclei move freely, uninhibited by atomic structure. Efforts to control nuclear fusion led to the development of experimental reactors, such as the tokamak, a device designed to contain plasma using powerful magnetic fields. The idea was to sustain fusion long enough to extract usable energy. Early experiments in the 1960s and 1970s demonstrated that fusion was possible in a controlled setting, but only for fractions of a second. The problem was keeping the plasma stable long enough to make fusion a viable energy source. Over the decades, fusion research continued, culminating in international projects like ITER, the world's largest nuclear fusion experiment. Located in France, ITER represents a collaborative effort by some of the world's leading scientific nations to finally make fusion power a reality. The goal is to create a self-sustaining plasma reaction that produces more energy than it consumes, a milestone known as ignition. But despite these advances, nuclear fusion remains elusive. The energy required to initiate and maintain fusion reactions still exceeds the energy produced. Technical challenges such as plasma instability, material degradation from extreme heat, and the immense cost of fusion research have slowed progress. Some scientists predict that commercial fusion energy could still be decades away, while others believe that breakthroughs in laser confinement or alternative reactor designs might accelerate the timeline. While fusion represents a hopeful future for clean energy, its potential remains unrealized. In the meantime, fission reactors continue to provide a significant portion of the world's electricity, despite their risks. The debate over nuclear power persists. Should we continue refining fission technology with its inherent dangers, or should we pour resources into the pursuit of fusion, even if a working reactor is still beyond our grasp? The story of atomic power is far from over. The atom, with all its potential for creation and destruction, remains both a marvel and a menace. Whether it ultimately leads to our salvation or our downfall will depend on how we choose to wield its power. Atoms, despite their fundamental role in shaping the universe, are not eternal. Their very nature dictates that over time, they break down, transforming into new elements or releasing their energy in bursts of radiation. This process, known as radioactive decay, is one of the most mysterious and essential forces in the cosmos, responsible for both creation and destruction on a massive scale. At the heart of radioactive decay lies the concept of atomic instability. Some atoms are stable, holding their structure indefinitely. Others, however, are doomed from the moment they form, their nuclei destined to change, disintegrate, or even split apart. The reason for this instability lies in the balance of forces within the atomic nucleus itself. Protons, all positively charged, naturally repel each other. Neutrons act as a buffer, helping to hold the nucleus together through the powerful but delicate nuclear strong force. When this balance is disrupted, the nucleus becomes unstable, setting the stage for decay. The process of decay is not uniform. It manifests in different forms, each with its own unique properties and consequences. Alpha decay, one of the simplest forms, occurs when an unstable nucleus ejects a cluster of 2 protons and 2 neutrons, a helium nucleus. This process reduces the atomic number of the element, transforming it into a completely new substance. Beta decay, on the other hand, involves the transformation of a neutron into a proton and the ejection of an electron, subtly altering the composition of the atom while preserving its overall structure. Perhaps the most mysterious and dangerous form of radioactive decay is gamma radiation. Unlike alpha and beta decay, which involve the emission of particles, gamma decay releases pure energy in the form of electromagnetic waves. These waves, highly penetrating and incredibly energetic, can pass through most materials, making them one of the most hazardous forms of radiation. The concept of half-life is key to understanding radioactive decay. Every radioactive element has a half-life, a fixed period in which half of a given sample will decay. Some isotopes, like carbon-14, have half-lives measured in thousands of years, making them useful for dating ancient artifacts and fossils. Others, like uranium-238, persist for billions of years, subtly shaping the geological and cosmic landscape. Then there are isotopes with fleeting half-lives, existing for mere fractions of a second before vanishing into new elements. But radioactive decay is not just a destructive force. It plays a crucial role in the cosmos, fueling the heat of planets, driving the life cycles of stars, and even influencing biological evolution on Earth. The very energy that sustains our planet's core and generates its magnetic field is largely due to the slow decay of radioactive isotopes buried deep within. Without this constant energy source, Earth's interior would have cooled long ago, and with it, the geologic activity that makes life possible. Yet, this slow disintegration is also an ever-present reminder of the impermanence of all matter. Atoms, even those seemingly eternal in their stability, will one day succumb to entropy. The very elements that compose the world around us were forged in the hearts of ancient stars, and through radioactive decay, they continue to evolve, shaping the destiny of the universe. Understanding this process is not merely a scientific endeavor, It is a glimpse into the fundamental nature of existence itself. Radioactive decay is not just a process that occurs in isolation. It is a fundamental mechanism that has shaped the universe itself. From the earliest moments of cosmic history to the present day, the breakdown of unstable atoms has influenced everything from planetary formation to the conditions necessary for life. It is a slow but relentless force, one that continues to sculpt the very fabric of reality. In the aftermath of the Big Bang, the universe was filled with a chaotic sea of subatomic particles. As the cosmos cooled, these particles began forming the first atoms, including hydrogen and helium, the two simplest and most abundant elements. However, heavier elements, like carbon, oxygen, and iron, did not exist in these early stages. They had to be forged in the nuclear furnaces of stars through a process called stellar nucleosynthesis. Yet even these newly formed elements were not entirely stable. Many of them contained too many or too few neutrons, making them radioactive. This instability set into motion a chain of events that would define the evolution of the cosmos. As radioactive isotopes decayed, they released energy, shaping the internal dynamics of planets, heating their cores, and influencing atmospheric conditions. Some of the most crucial elements for life, including potassium-40 and uranium-238, are radioactive and have played a direct role in the development of Earth's environment. One of the most significant ways radioactive decay has influenced the Earth is through its impact on planetary geology. The slow decay of elements like uranium, thorium, and potassium, deep within the Earth's mantle, has been responsible for maintaining geothermal activity for billions of years. This heat drives plate tectonics, which in turn influences everything from the formation of mountains to volcanic eruptions and earthquakes. Without the heat generated by radioactive decay, the Earth's interior would have solidified long ago, leading to a geologically stagnant world devoid of the dynamic processes that make life possible. But the role of radioactive decay extends beyond just geology. It has also been instrumental in the emergence of life itself. The constant exposure to radiation from naturally occurring isotopes has contributed to genetic mutations over millions of years, driving the process of evolution. While high doses of radiation can be lethal, low levels of background radiation have been a subtle but persistent factor in the diversification of life on Earth. By altering DNA, radiation-induced mutations have provided the raw material for natural selection to act upon, allowing species to adapt to their environments and evolve over time. In addition to shaping life on Earth, radioactive decay has been a key player in our understanding of time itself. The science of radiometric dating has allowed scientists to determine the age of ancient artifacts, fossils, and even the planet itself. By measuring the decay of isotopes like carbon-14, potassium-argon, and uranium-lead, researchers can estimate the age of organic materials and geological formations with remarkable accuracy. This has provided invaluable insights into the history of our world, from the extinction of the dinosaurs to the timeline of human civilization. Despite its many natural and beneficial roles, radioactive decay also presents a significant hazard. The radiation emitted during decay processes can be highly dangerous to living organisms. Alpha particles, though relatively weak in penetration, can cause severe damage to cells if inhaled or ingested. Beta particles, being more penetrating, can pass through skin and damage internal tissues. Gamma radiation, the most dangerous of all, can penetrate deep into the body, altering cellular structures and increasing the risk of cancer. This dual nature of radioactive decay, as both a creative and destructive force, is evident in its role in nuclear energy. While controlled radioactive decay is harnessed in nuclear reactors to generate electricity, uncontrolled decay can lead to catastrophic events like nuclear meltdowns. The disasters at Chernobyl and Fukushima serve as grim reminders of what happens when the delicate balance of nuclear reactions is lost. The release of massive amounts of radiation during such events can render entire regions uninhabitable, contaminating air, water, and soil for generations. Despite these dangers, the use of radioactive materials in medicine, industry, and scientific research has provided immense benefits to humanity. In medicine, radioactive isotopes are used in imaging techniques like PET scans to diagnose diseases, while radiation therapy is used to treat certain types of cancer. In industry, radioactive tracers help detect leaks in pipelines, sterilize medical equipment, and improve the durability of materials. Even space exploration has relied on radioactive decay, with plutonium-238 powering long-duration missions like the Voyager probes, which continue to transmit data from the outer reaches of the solar system. As we continue to study radioactive decay, new questions emerge. Could there be yet undiscovered elements or isotopes with unique properties? How does radiation exposure affect organisms over long timescales? And perhaps most intriguingly, could radioactive decay play a role in the ultimate fate of the universe itself? These questions push us toward the next great unknown, for while radioactive decay has shaped our world and beyond, its consequences stretch far into the distant future, beyond planets, beyond stars, beyond even time itself. Radioactive decay is not just a terrestrial phenomenon, it plays a crucial role in the grand cosmic scale of the universe. From the lifespans of stars to the decay of entire planets, the influence of radiation extends across time and space, dictating the eventual fate of everything that exists. Even now, as we look deep into the cosmos, we see the fingerprints of atomic instability woven into the very structure of reality. One of the most profound examples of radioactive decay's impact on the universe is its role in stellar evolution. Stars, the celestial engines that power the cosmos, owe their lifespans and explosive deaths to nuclear processes, including radioactive decay. As stars burn through their nuclear fuel, they fuse lighter elements into heavier ones, eventually forming elements like iron and nickel in their cores. But this process has a limit. Once a star's core becomes saturated with iron, fusion ceases to generate energy. The equilibrium that holds the star together collapses, leading to one of the most violent events in the universe, the supernova. Supernovae are more than just cataclysmic explosions. They are the crucibles in which the universe's heaviest elements are forged. When a massive star dies, the energy released in the explosion is so intense that it produces elements heavier than iron, such as uranium, thorium, and plutonium, many of which are radioactive. These newly formed elements are scattered into space, seeding the next generation of stars, planets, and eventually, life itself. In a sense, the radioactive isotopes that now decay within Earth's crust were created billions of years ago in the deaths of ancient stars. The heavy elements necessary for the formation of rocky planets and biological life would not exist without the cycles of stellar birth, death, and decay. Every atom of gold, uranium, and carbon in existence today was forged in the violent heart of an exploding star, linking the fate of radioactive elements to the cosmic cycle of creation and destruction. But beyond stars and planets, there is an even more unsettling role that radioactive decay might play: the potential demise of the universe itself. Some physicists believe that, on a long enough timescale, even the most stable atomic particles will eventually decay. While protons, the fundamental building blocks of atoms, have long been thought to be stable, some theories suggest that they too may eventually disintegrate through an incredibly slow process known as proton decay. Proton decay is purely theoretical at this point. No experiment has yet confirmed its existence. However, if it is real, it means that the universe as we know it is not permanent. Given enough time, trillions upon trillions of years, even atoms themselves would cease to exist. Matter, in its current form, would vanish, leaving behind only a cold, empty void. This concept ties into the broader idea of the heat death of the universe, a scenario in which all energy is evenly distributed and no further work can be done. In this ultimate endgame, the last vestiges of radioactive decay would be the only flickers of activity in an otherwise lifeless cosmos. But could radioactive decay also hold the key to cosmic rebirth? Some theories suggest that extreme radiation levels in the early universe could have created conditions ripe for the formation of new exotic particles, perhaps even giving rise to new universes in a cycle of endless renewal. While such ideas remain speculative, they highlight the enigmatic nature of radiation and decay. Is it merely a force of destruction, or does it serve as a fundamental mechanism for cosmic rebirth? Closer to home, radioactive decay also plays a role in our search for extraterrestrial life. Scientists studying distant exoplanets look for the presence of elements like uranium and thorium, as these radioactive materials generate heat that can sustain geological activity. Planets with active interiors are more likely to have volcanoes, magnetic fields, and atmospheres, all key ingredients for life as we know it. Without the energy provided by radioactive decay, many planets would be cold, stagnant worlds incapable of supporting complex chemistry. Additionally, understanding radioactive decay has become essential in our quest to explore the universe. Deep space missions rely on radioisotope thermoelectric generators, RTGs, which convert the heat produced by decaying plutonium-238 into electricity. This technology has powered some of the most distant spacecraft ever built, including the Voyager probes, which continue their journey beyond the solar system. In a sense, radioactive decay is what allows us to extend our reach into the unknown, fueling our machines as they travel through the vast emptiness of space. Yet, for all its cosmic significance, radioactive decay remains a force that humanity has yet to fully master. Our attempts to control it, through nuclear power, medical applications, and scientific research, have yielded both incredible benefits and devastating consequences. Radiation exposure continues to be a threat, nuclear waste remains a challenge, and the ethical dilemmas surrounding nuclear weapons persist. As we continue to push the boundaries of science, one thing remains clear: radioactive decay is far more than just the slow breakdown of atoms. It is a process that has shaped planets, driven evolution, and perhaps even set the stage for the ultimate fate of the universe. Whether it will lead to destruction or rebirth remains one of the great unanswered questions of physics. What we do know is that radioactive decay is one of the most fundamental and unavoidable forces in existence. It has been with us since the beginning. It continues to shape our world, and it will persist long after our species, our planet, and even our stars have faded into the darkness. In the grand scheme of the cosmos, the disintegration of atoms is not an end, but rather a transformation, one that has, and always will, define the very nature of reality. The universe, vast and seemingly eternal, is governed by fundamental laws, laws that dictate how energy moves, how matter interacts, and ultimately, how everything must come to an end. Among these laws, none are more inexorable than the second law of thermodynamics, the principle that ensures the eventual fate of all things: entropy. This universal force drives the cosmos toward disorder, and if left unchecked, it will one day lead to the most chilling prospect imaginable: the heat death of the universe. Entropy is the measure of disorder in a system. In any closed system, energy naturally spreads out, shifting from ordered states to increasingly chaotic ones. On a small scale, we see this in everyday life. A hot cup of coffee cools down, a battery loses its charge, and ice melts into water. Over time, energy disperses, and unless it is replenished, a state of balance, of uselessness, is reached. This same principle applies to the universe itself. In the earliest moments of existence, the universe was a place of extreme order, a seething hot plasma teeming with energy in a compact and highly organized state. But as it expanded, the energy that once concentrated in one place began to spread. Galaxies formed, stars ignited, and the intricate dance of atomic interactions gave rise to planets, life, and everything we know. Yet with each passing moment, the energy available for useful work diminished. Stars burned their fuel, radiation was emitted into space, and the universe marched slowly but inevitably toward a state where all motion, all light, and all structure would cease. This final state, the heat death, describes a future in which entropy has reached its maximum and no useful energy remains. It is a scenario in which temperature differences no longer exist, meaning no further work can be done. With every atom approaching the same level of energy, the universe will become a stagnant, featureless void, a place where even the fundamental interactions of matter cease. The seeds of this fate are already evident. Every star that burns is gradually depleting its fuel, converting mass into energy and expelling it into space. Over billions of years, even the most massive stars will exhaust their nuclear reactions, either collapsing into dense remnants like black holes and neutron stars, or dispersing into space as cooling white dwarfs. The once vibrant cosmos will dim as fewer and fewer stars remain to illuminate the darkness. But even after the last star fades, the process does not stop. Matter itself is not exempt from the relentless march of entropy. Subatomic particles, the very building blocks of atoms, may one day decay into even more fundamental components. The stability of protons, long thought to be unbreakable, is now questioned by some physicists. If protons have a finite lifespan, however long it may be, then even atoms themselves will eventually cease to exist. The decay of protons would mark the true beginning of the end, as the very structure of matter disintegrates. Once all atomic nuclei have broken down, only isolated electrons, positrons, and low-energy radiation will remain, floating aimlessly through a universe grown impossibly vast and immeasurably cold. The cosmic microwave background radiation, once a remnant of the Big Bang's heat, will be stretched so far by the universe's expansion that it will be indistinguishable from the void itself. Some scientists theorize that black holes, the last great reservoirs of concentrated matter, might endure far beyond the demise of ordinary atoms. These titanic objects, created by the collapse of massive stars, trap everything that crosses their event horizons, hoarding energy and mass in their gravitational grip. But even black holes are not eternal. According to Stephen Hawking's groundbreaking work, black holes slowly evaporate due to a process called Hawking radiation. Over time, they leak energy and mass into space until, at last, they vanish completely. This phase of the universe will be one of true stillness, an existence without heat, without movement, without any means of change. It will be a cosmos where entropy reigns supreme, where every form of energy has been expended, and where the potential for anything new to emerge has been erased. In this frozen wasteland, the cosmos will persist in a state of absolute equilibrium, devoid of the very forces that once brought it to life. Yet even in this bleak forecast, questions remain. Could some exotic physics emerge at the final stages of entropy? Could hidden structures, unknown forms of matter, or unforeseen quantum effects create a new cosmic cycle? Some speculative theories suggest that deep within the fabric of the vacuum, instability could give rise to new universes, triggering a rebirth from the ashes of the old. For now, however, the evidence suggests a far more unsettling reality. A universe that, after an unfathomable stretch of time, will simply fade into cold, eternal darkness. The heat death of the universe may be its final and ultimate fate, a destiny written into the very laws of physics from the moment time began. The heat death of the universe is not a singular event, but a slow, relentless process stretching across an incomprehensible expanse of time. It is a journey through cosmic decay, where the intricate structures that once filled the universe, galaxies, stars, planets, and even atoms, gradually dissolve into a barren void. To understand this final fate, we must explore the universe's long and inevitable decline, step by step. as it progresses toward its ultimate equilibrium. The first stage in this descent is the end of star formation. Stars are born when dense clouds of gas collapse under gravity, igniting nuclear fusion in their cores. This process has been ongoing for billions of years, with new stars forming as old ones die. However, as galaxies exhaust their reserves of hydrogen, the primary fuel for star formation, the birth of new stars will eventually cease. Astronomers predict that in about 100 trillion years, star formation will grind to a halt. The universe will then enter an era dominated by aging, dying stars with no new ones to replace them. As time marches forward, the once bright cosmos will grow steadily darker. The most massive stars will die first, ending their lives in spectacular supernova explosions that create neutron stars and black holes. Smaller, sun-like stars will eventually become white dwarfs, dense, smoldering remnants that no longer produce energy through fusion. Over the next quadrillion years, even these fading embers will cool, turning into cold black dwarfs, stellar remnants so dark and inert that they are nearly indistinguishable from the space around them. With no new energy sources, galaxies will begin to drift apart. The expansion of the universe, driven by dark energy, will continue to accelerate, causing distant galaxies to recede further and further from one another. Eventually, the observable universe will shrink, as the accelerating expansion stretches space itself to the point where galaxies beyond our local group will disappear from view. The cosmos will become a lonely place, with only isolated remnants of matter scattered across an ever-growing void. As the last stars fade, another process will dominate: the slow decay of matter itself. While we often think of atoms as stable, some theories suggest that even protons, the fundamental building blocks of matter, are not eternal. If protons do decay, their half-life is estimated to be at least 10 to the 34th years, an almost inconceivably long time. But given an infinite timeline, even the most improbable decay events will eventually occur. One by one, protons will break apart, converting into lighter particles such as positrons and neutrinos, which will dissipate into space. If proton decay is real, then over the course of 10 to the power of 40 years, all the remaining atoms in the universe will vanish, leaving behind only a sparse collection of electrons, neutrinos, and low-energy photons. At this stage, planets, asteroids, and even the last frozen remnants of stars will have disintegrated into their most elementary components. The universe will be a featureless sea of subatomic particles, barely distinguishable from the vacuum itself. But there is still one more act in this slow cosmic demise: the evaporation of black holes. For a long time, black holes will dominate what remains of the universe. These massive objects, formed from the collapse of the universe's heaviest stars, will continue to pull in any remaining matter, devouring whatever is left. However, even black holes are not immune to entropy. Stephen Hawking's work on Hawking radiation suggests that black holes slowly lose mass over time as they emit faint radiation due to quantum effects at their event horizons. This process is almost imperceptible for large black holes, but over timescales of 10 to the power of 100 years, even the most massive black holes will gradually evaporate, radiating away their energy particle by particle. The largest supermassive black holes, the remnants of ancient galaxies, will be the last to disappear, marking the final major event before the universe enters its ultimate unchanging state. At this point, what remains is a vast cold void filled with a diffuse soup of low-energy photons and elementary particles. With all matter gone, there will be no more energy gradients, no temperature differences, and no possibility of physical interactions. The cosmos will have reached maximum entropy, a state where no useful energy remains to drive any further change. This is the true heat death of the universe, a time when even the concept of time itself may lose meaning, as nothing remains to mark its passage. And yet, even in this bleak and final state, some theoretical physicists speculate that unknown physics could emerge in the deep future. Quantum fluctuations in the vacuum of space, or the possibility of a false vacuum collapse, could potentially trigger the birth of a new universe. While this remains purely speculative, it suggests that the end of one universe may not necessarily mean the end of all existence. But for now, based on our current understanding of physics, the heat death of the universe appears to be an inescapable reality, a fate dictated by the unyielding march of entropy, where even atoms themselves are doomed to disappear into the cold, silent abyss of eternity. With the final evaporation of black holes and the decay of all matter, the universe will have entered an era unlike anything that has come before. This is the deep future, a time so far removed from our present that even the concept of time itself begins to lose meaning. Every structure, every force, every fundamental aspect of the cosmos as we understand it will have faded into the background, leaving behind nothing but the faintest echoes of what once was. What remains in this final epoch is a universe filled with a diffuse sea of low-energy photons, neutrinos, and other elementary particles. Without stars, without planets, without even the smallest remnants of atomic matter, the universe will have settled into an equilibrium where no further change is possible. This is the true definition of maximum entropy, a state where all energy is evenly distributed and nothing remains to power the processes that once drove the evolution of galaxies, stars, and life itself. It is a vision of ultimate stillness, a place where nothing happens, because nothing can happen. In thermodynamic terms, all useful energy has been spent. There are no more temperature differences to drive movement, no more forces capable of shaping matter, and no remaining potential for new structures to form. The universe has effectively died, not with a violent collapse, but with an eternal, unchanging silence. Yet, even in this seemingly hopeless future, the laws of physics leave room for uncertainty. One of the most speculative but fascinating ideas proposed by physicists is the possibility of quantum fluctuations in the vacuum of space. In quantum mechanics, even an empty vacuum is not truly empty. Instead, it is a seething ocean of virtual particles, popping in and out of existence on imperceptible timescales. Over vast stretches of time, far beyond anything we can currently comprehend, could such fluctuations lead to something new? One possibility is the spontaneous creation of new universes. Some theories suggest that the vacuum state of space is not entirely stable. Given enough time, a rare and random fluctuation could create a localized bubble of lower energy, perhaps a region of space where the laws of physics are different from our own. If this bubble expanded rapidly, it could seed the birth of an entirely new universe, much like how cosmologists believe our own universe began with the Big Bang. Another speculative idea is that of a false vacuum decay. If our universe exists in a metastable energy state rather than a truly stable one, a quantum event could trigger a shift to a lower energy level, causing space itself to collapse in an instant. This scenario, known as vacuum decay, would destroy everything instantly, replacing our universe with a different set of physical laws. While terrifying in concept, such an event is unlikely to happen for many trillions of years, if ever. But perhaps the most unsettling realization is that, even if no such rebirth occurs, time itself may cease to have meaning in a universe without change. In the absence of events, movement, or interactions, the passage of time becomes irrelevant. The universe would not just be frozen, it would be timeless, an endless expanse where the distinction between past, present, and future vanishes. What does existence mean in a place where nothing ever happens? This is a question science cannot yet answer. Some theorists have proposed that in the deepest reaches of time, new physics could emerge. Laws of nature that only become apparent under extreme conditions of entropy and cold. Could unknown forces arise to counteract the spread of disorder? Could exotic particles or states of matter exist in ways we cannot yet imagine? While there is no evidence for such phenomena, the history of physics has repeatedly shown that the universe is full of surprises. For now, based on our current understanding, the heat death of the universe remains the most likely final fate of reality. It is an ending dictated not by any external force, but by the inescapable mathematics of entropy itself. Every reaction, every movement, every structure has ultimately contributed to the spreading out of energy, ensuring that one day, nothing will remain but the cold remnants of a universe long past its prime. And yet, the story of the universe has always been one of transformation. Stars are born and die, elements form and decay, civilizations rise and fall. From the violent beginnings of the Big Bang to the quiet dissolution of atoms, everything that exists follows a pattern of change. If that change can occur once, could it happen again? Could something, someday, emerge from the quiet void? Perhaps we are not witnessing the true end of the universe, but merely another transition, one beyond our capacity to understand. The heat death may be the final chapter as we currently perceive it, but in a cosmos governed by uncertainty and infinite time, even the end may not be absolute. For now, though, the universe drifts toward its inevitable fate, a place without light, a place without movement, a place where even the fundamental particles of matter are nothing more than ghosts in the void. A universe that was once alive with energy, creation, and change will, at last, fall silent. The universe is built upon the familiar building blocks of matter, protons, neutrons, and electrons, forming the elements that shape everything from the air we breathe to the stars that light the night sky. But what if this traditional form of matter is not the only way existence can manifest? Are there exotic, unconventional states of matter that could defy decay, persist beyond the heat death of the universe, or even reshape our understanding of physics itself? Modern science suggests that reality may be far stranger than we once imagined. Theories in particle physics, quantum mechanics, and cosmology have uncovered hints that exotic states of matter could exist, substances that operate outside the normal rules governing protons, neutrons, and electrons. These bizarre forms of matter might be nearly indestructible, immune to decay, or even capable of surviving the death of all known matter. One of the leading candidates for such an exotic state is strange matter, a theoretical substance composed of strange quarks. In ordinary matter, protons and neutrons are made up of two types of fundamental particles called up and down quarks. But under extreme conditions, such as those found in the core of neutron stars, scientists believe that matter could be compressed into an entirely new state where strange quarks take over, forming what is known as strange matter. What makes strange matter truly exotic is its theoretical stability. Unlike ordinary matter, which is prone to radioactive decay and eventual proton breakdown, strange matter could be incredibly stable, perhaps even more so than regular atoms. Some theories suggest that if a single nugget of strange matter were to come into contact with normal atomic matter, it could trigger a chain reaction, converting ordinary nuclei into more strange matter. This hypothetical process, sometimes called strangelet formation, has led to speculation about whether strange matter might already exist in some regions of the universe, hidden within neutron stars or cosmic remnants. Neutron stars themselves are a fascinating example of an extreme state of matter. These collapsed stellar cores are some of the densest objects in the universe, with a single teaspoon of neutron star material weighing as much as a mountain on Earth. Inside their cores, matter is squeezed so tightly that atoms can no longer exist in their normal form. Instead, protons and electrons merge into neutrons, forming a sea of degenerate nuclear material. But deeper inside, even neutrons may not be stable, giving way to quark matter, where individual quarks roam free in a dense, exotic plasma. If strange quark matter exists at the core of neutron stars, it raises profound questions. Could strange matter be a more fundamental form of matter, one that is immune to the normal processes of decay that eventually destroy atoms? Could it last for eternity, even as normal matter fades away? And if so, could remnants of strange matter survive beyond the heat death of the universe, acting as the last remaining objects in an otherwise empty cosmos? Another exotic state of matter that could play a role in the ultimate fate of the universe is dark matter. Unlike normal matter, dark matter does not interact with light, making it invisible to traditional observational techniques. Yet its gravitational effects can be seen across the cosmos, influencing the motion of galaxies and shaping large-scale cosmic structures. While the exact nature of dark matter remains unknown, its apparent stability suggests that it may not be subject to the same decay processes that govern normal atoms. Some theories propose that dark matter is composed of WIMPs, weakly interacting massive particles, hypothetical particles that could pass through ordinary matter without leaving a trace. Others suggest that dark matter might consist of axions, ultra-light particles that could form an invisible field stretching across the universe. If dark matter is made of particles that do not decay, then it could outlast all known forms of ordinary matter, persisting long after stars, planets, and atoms have faded into oblivion. An even more radical possibility is that dark matter is not composed of particles at all, but instead represents a different kind of matter altogether, something beyond our current understanding of physics. Could dark matter be a manifestation of exotic physics that allows it to exist indefinitely? Could it hold the key to escaping the slow decay of the universe? Moving beyond dark matter, physicists have also speculated about Planck-scale exotic matter, an ultra-dense form of matter that could exist at energy levels approaching the Planck scale, the theoretical limit where gravity and quantum mechanics merge. If such matter exists, it might be immune to the processes that lead to atomic decay. It could be composed of topological defects, stable structures that resist disintegration due to the geometry of space-time itself. Another extreme form of matter that could defy conventional destruction is Bose-Einstein condensates. These substances, created in laboratories at temperatures near absolute zero, behave in strange and counterintuitive ways. In this state, individual atoms merge into a single quantum entity, behaving as a unified wave rather than as separate particles. While Bose-Einstein condensates are fragile under normal conditions, could some unknown cosmic mechanism create an indestructible version of such matter? Could it represent a new phase of existence that emerges when the universe reaches extreme cold and stillness? Beyond exotic particles and quantum states, some physicists speculate about the possibility of negative energy matter, substances that react in opposition to gravity, repelling rather than attracting. While no confirmed examples of negative energy matter exist, its theoretical properties have been explored in concepts like warp drives and wormholes, suggesting that such matter could hold the key to circumventing the laws of entropy. If negative energy matter exists, it might be able to counteract the effects of heat death, creating local pockets of order within an otherwise decaying universe. Some physicists speculate that exotic forms of matter like these could serve as seeds for a future cosmos, triggering a new phase of expansion or even creating new universes. While many of these ideas remain speculative, they highlight an important truth. The universe may hold secrets far beyond what we currently understand. Matter, in its conventional form, may not be the final word on existence. Instead, the universe may harbor states of matter so exotic, so resilient, that they transcend the very limits of entropy and decay. If such matter exists, it could change our understanding of the cosmos, revealing new pathways for survival in a universe otherwise doomed to fade away. Whether through strange quark matter, dark matter, or yet undiscovered exotic substances, the possibility remains that some form of matter could outlast the destruction of everything else, defying the slow death that physics seems to predict. And if the universe does contain such matter, it raises an even greater question. Could these exotic materials hold the key to restarting the cosmic cycle, ensuring that even in the deepest reaches of time, something will always remain? While exotic forms of matter like strange quark matter and dark matter challenge our understanding of the universe, even more radical possibilities exist, ones that stretch the boundaries of known physics and hint at forms of matter capable of surviving the very fabric of space-time itself. Could there be materials that exist outside the standard model of physics? Could some undiscovered state of matter provide a refuge from entropy, defying the slow disintegration of everything we know? One of the most intriguing possibilities is the existence of primordial black hole relics. While black holes are known to slowly evaporate due to Hawking radiation, some theoretical models suggest that extremely small black holes, formed in the intense conditions of the early universe, could leave behind ultra-stable remnants once they shrink beyond a certain size. Unlike traditional black holes, which radiate away their energy until they vanish, these remnants would no longer emit significant radiation and could persist indefinitely. If such objects exist, they might be among the last surviving structures in a universe approaching heat death. Even more fascinating is the idea that these black hole remnants could serve as a form of exotic matter storage, containing unknown quantum states preserved beyond normal decay. Some physicists speculate that remnants could trap information inside them, shielding it from the entropic forces that erase all other structures. If true, these remnants might not only defy destruction, but could also act as time capsules, carrying traces of past universes into the distant future. Beyond black holes, another mind-bending concept is that of stable wormhole structures. In theoretical physics, wormholes are shortcuts through space-time, allowing for the possibility of instant travel between distant points. While most wormhole solutions are unstable, requiring exotic negative energy matter to remain open, some models suggest that certain topological configurations of spacetime might allow for naturally stable wormholes. If such structures exist, they could persist long after the rest of the universe has faded into cold equilibrium. Could stable wormholes serve as refuges from entropy? Could they provide gateways to regions of the cosmos untouched by the heat death, or even into entirely new universes? While such ideas remain speculative, they point to a deeper question. Are there hidden aspects of physics that allow certain structures to persist indefinitely, even when all else has decayed? One of the most extreme possibilities in physics is the existence of Boltzmann brains, self-aware entities that emerge purely from quantum fluctuations. In an infinitely old universe approaching heat death, random fluctuations in the vacuum could, in theory, create temporary islands of order, where matter spontaneously assembles into complex configurations, potentially even conscious minds. This idea, named after the physicist Ludwig Boltzmann, suggests that in a universe where entropy has reached its maximum, the only remaining sources of complexity may arise from statistical improbabilities. Given enough time, could quantum randomness assemble a fully formed brain, one that contains memories, thoughts, and a sense of existence, even in a universe devoid of life? While the idea of Boltzmann brains is deeply unsettling, it raises profound philosophical questions. If consciousness can emerge from random fluctuations, is reality itself merely a fleeting moment in an otherwise chaotic void? Could exotic forms of matter or energy be harnessed to create and sustain ordered structures beyond heat death, giving rise to new forms of existence? Some physicists have also proposed that new laws of physics could emerge under extreme entropy. Just as the early universe underwent phase transitions, where fundamental forces split apart from a unified state, the distant future may hold similar transitions, where matter and energy behave in ways we cannot yet predict. Could the fabric of space-time restructure itself, creating new states of matter that are stable under entirely different conditions? One speculative concept is the idea of false vacuum decay triggering a new cosmic epoch. If our current universe exists in a metastable energy state rather than a truly stable one, a sudden quantum event could cause space itself to collapse into a new, lower energy state. In such a scenario, what we perceive as empty space might be replaced by an entirely new physics, potentially giving birth to exotic matter forms that are impervious to decay. Alternatively, some models suggest that information itself may be the key to survival in a universe facing heat death. In the field of digital physics, some theorists propose that the fundamental nature of reality is not material, but informational, meaning that the universe could be viewed as a vast computational structure. If true, then preserving information might be the ultimate way to defy entropy. Could advanced civilizations one day encode themselves into self-sustaining quantum fields or exotic substrates of spacetime, persisting even as normal matter fades away? Another speculative but compelling idea is that of space-time crystals, structures that exist not just in space, but in time itself. These hypothetical materials, first proposed in the 2010s, would exhibit perpetual motion at a quantum level, constantly cycling through states without expending energy. Unlike normal matter, which succumbs to entropy, a space-time crystal could theoretically persist indefinitely, never settling into equilibrium. If such matter exists naturally in the cosmos, it could provide an entirely new way for energy and structure to endure beyond the lifespan of ordinary atoms. The search for exotic matter capable of defying destruction is ultimately a search for new principles of physics. Could matter exist in states that never decay? Could unknown quantum effects allow for self-sustaining patterns of information? Could the structure of space-time itself be engineered to prevent the spread of entropy? While many of these ideas remain firmly in the realm of speculation, the mere possibility that matter could escape destruction challenges our deepest assumptions about the fate of the universe. If such matter exists, it could mean that not everything is doomed to fade away, that something, however small or alien, will endure beyond the last flickers of normal matter. And if even a single exotic form of matter can persist through the death of the universe, then it opens the door to an even greater mystery. Could such matter serve as the foundation for whatever comes next? The story of atoms is a story of creation and annihilation, of endurance and inevitable decay. It is a paradox woven into the very fabric of existence. The same forces that build the universe are also the ones that will one day tear it apart. From the moment atoms first formed in the aftermath of the Big Bang, they were already marching toward their destruction. And yet, across the cosmic timeline, they have shaped galaxies, ignited stars, given rise to life, and built civilizations. But in the grand scale of the universe, even these fundamental building blocks are fleeting, destined to dissolve into nothingness. Yet, if the nature of reality has taught us anything, it is that destruction is never the end, it is only transformation. Matter, energy, and space-time itself are locked in an endless cycle of change, shifting between states in ways we are only beginning to comprehend. Is entropy truly the final fate of the universe? Or could there be something beyond the slow dissolution of all things? When we peer into the distant future, the universe appears to be heading toward its inevitable heat death. The stars will burn out, galaxies will unravel, and even atoms themselves will decay into subatomic remnants, drifting in an ever-expanding void. The cosmos will be stripped of all complexity, reduced to a silent, dark expanse where no forces remain to shape the future. It is a haunting vision, one in which the very essence of existence itself is wiped away, leaving behind nothing but a featureless sea of radiation and particles too cold to interact. But there is something deeply unsatisfying about the idea of a universe with no future. Throughout history, whenever humans believed they had reached the limits of understanding, new discoveries shattered those assumptions. Could the same be true for the fate of the universe? The very forces that lead to destruction, the instability of atoms, the decay of matter, and the inevitable spread of entropy, may contain within them the seeds of rebirth. Strange forms of matter, exotic physics, and unknown quantum processes could provide an escape from cosmic oblivion. Dark matter, strange quark matter, and space-time crystals hint at states of existence that defy our conventional understanding. Could such forms of matter be the last remnants of an otherwise dying universe, persisting long after ordinary atoms have faded? Could they serve as a foundation upon which something new could emerge? Even more radical ideas suggest that the death of one universe could give rise to another. Some theories propose that at the deepest level of reality, the vacuum of space itself is not truly empty. It is a shifting sea of quantum fluctuations, constantly birthing and destroying particles in an endless dance. In an unimaginably distant future, could one of these fluctuations ignite a new Big Bang, seeding a fresh cosmos from the ashes of the old? If so, could some remnant of information, energy, or structure carry over from one universe to the next? It is possible that the story of existence does not end with a silent, lifeless void, but rather with a transition into something we cannot yet comprehend. Some physicists speculate that time itself may not be an absolute, but rather a property of the universe that can emerge and disappear under different conditions. Could there be states of existence where time ceases to function as we know it, allowing for new, unforeseen processes to take shape? Could the heat death of our universe merely be a shift into a phase of reality that operates under completely different principles? If there is one certainty, it is that the universe is more mysterious than we can imagine. From the smallest subatomic particles to the largest cosmic structures, nature has continually defied our expectations. Atoms, once thought to be the indivisible foundation of all matter, turned out to be mere stepping stones to deeper layers of reality. Quarks, neutrinos, quantum fields, and beyond. If the history of scientific discovery has shown us anything, it is that each time we believe we have reached the limits of knowledge, the universe reveals yet another hidden layer beneath. So perhaps the question is not whether the universe will end, but whether endings truly exist at all. Perhaps the dissolution of atoms is not an extinction, but a transformation, one that is simply beyond our current ability to perceive. The cycle of destruction and creation may stretch far beyond anything we can comprehend, operating on scales of time and space that render human understanding meaningless. And yet, within this vast and indifferent cosmos, we exist, thinking, questioning, searching for meaning in the grand machinery of the universe. We are made of atoms, forged in the hearts of dying stars, shaped by the very processes of creation and decay that define existence itself. For a fleeting moment in cosmic time, these atoms have assembled into something capable of understanding them, of marveling at their power and their fate. Even if atoms are doomed to disappear, even if the universe fades into the darkness of entropy, our brief awareness of it all is, in itself, something profound. We are witnesses to the cosmic story, momentary participants in the grand unfolding of reality. And whether the universe truly ends, transforms, or begins anew, our role in it, however small, has mattered. So, as we look toward the future, knowing that even the most fundamental particles will one day fade away, we must ask, is this truly the end? Or is it merely another transition, waiting for us to discover what comes next? Perhaps, in the great silence that follows, the universe will whisper a new beginning. Thank you for joining us on this extraordinary journey through the cosmos, here on Frontiers of Infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us each Friday at 7 p.m. Eastern, where we unravel the darkest mysteries of space.